ওই ইকুয়েশনটা বুঝতে অসুবিধা হচ্ছিল, কারণ ম্যাম আমরা 12 এ পড়ে এসেছিলাম আইসি ইকুয়ালস টু বিটা আইবি,
হ্যাঁ
ওই প্লাস প্লাস আইসিও ওই টার্মটা একটু যদি ক্লিয়ার করে
কম্পোনেন্টটা
দেন।
পড়নি। হ্যাঁ আজকেই আমি এই লিকুইড ক্রিস্টাল ডিসপ্লেটা খালি বাকি আছে
হ্যাঁ
অপটোইলেকট্রনিক ক্যাটাগরি, এটা হয়ে গেলেই আজকে বিজেটি শুরু করবো, কেমন? তখন এটা ক্লিয়ার হয়ে যাবে। তবু বলছি আপাতত এই জিনিসটা মানে কি তোমার, ভেরি সরি হ্যাঁ, প্রত্যেকে এটা কারেক্ট করে নিও না, common emitter configuration. So base is input, collector is output. Output current is related to this one, base by this. তার মানে as a proportional linear, তাই না? IC proportional to IB, beta is the proportionality constant, the gain. এবার if we keep our input open, তার মানে কোনো বেস কারেন্ট দিচ্ছি না, বায়াস করিনি বেস এমিটারে, হ্যাঁ, তাহলে IB is 0, then IC should be 0 in absence of IB. But এখানে যখন আমরা ইনপুটে কিছু সিগন্যাল দিইনি, কোনো বায়াসও দিইনি, still this is the collector based junction is a reverse bias junction. কালেক্টরের এই সাপ্লাইটা কিন্তু আছে, ইনপুটটার ভিবিটার কি বিবি বেসের সাপ্লাইকে আমি লাগাই, এইটার জন্য আমার কালেক্টর বেস জাংশন রিভার্স বায়াসড হয়ে আছে, NPN, N টাইপ ইজ পজিটিভ। তাহলে এই যে রিভার্স বায়াস হওয়ার ফলে এখানে একটা ডিপ্লিশন রিজিয়ন ক্রিয়েটেড হবে। নাও আমরা জানি যে একটা রিভার্স বায়াস পিএন জাংশনে যে থার্মালি জেনারেটেড ক্যারিয়ারের জন্য একটা কারেন্ট ফ্লো করে, that will also be present here. So that this part is that component which will depend on temperature and it is constructed by the electron and hole component, thermally generated electron and holes. So it's a nominal, যেমন তোমরা রিভার্স বায়াস ডায়োডে দেখেছো of the order of microamp, whereas forward biasটা মিলিঅ্যাম্প, এখানেও তাই। যখন এটা নেই আইবি দিইনি, in that case it is the only component, but তখন আমরা এটাকে ধরছি, but in presence of IB this component will be too large, beta becomes of the order of 100, তখন আর এই কম্পোনেন্টকে আমরা ইগনোর করি, বললে কি দাঁড়ায় এই লিনিয়ার রিলেশনশিপটা ভ্যালিড, সো উই ইউজ ইট ফর অ্যাম্প্লিফিকেশন। এইটা আমি আজকে বিজেটি পড়াবো, আর একটু ডিটেলসে যাব, ফর দ্য টাইম বিং এটা অ্যাকসেপ্ট করলে কুশল?
ম্যাম তাহলে ওই আইবি
এইটা
ম্যাম মানে আমি বলছি যে কালেক্ট
শুনতে পাচ্ছি না, বলুন কি বলছো? হ্যালো
ম্যাম বলছি যে ইনিশিয়ালি একটা রিভার্স বায়াস থাকছে ফ্রম এন টু পি ডিউ টু ভিসিসি সোর্স, আর তারপরে ডিউ টু থার্মালি জেনারেটেড ইলেকট্রন হোল পেয়ার ওটা ড্রিফট করে আসছে, যে কারণে ওই কারেন্ট কম্পোনেন্টটা আসছে।
ড্রিফট করে আসছে, হ্যাঁ, থার্মালি জেনারেটেড ক্যারিয়ার ড্রিফট অ্যাক্রস দ্য রিভার্স বায়াস জাংশন। দেখো আজকে বিজেটিটা পড়াই, তারপর ক্লিয়ার হবে। তোমার ইনপুটটা এই বেসিক্যালি কি হয়, এমিটার এমিটস, কালেক্টর কালেক্টস, সো এমিটার ক্যারিয়ার ইনজেক্ট করে, তার মানে এই দিকটা আমার ফরওয়ার্ড বায়াস করতে হয় ইনপুট সাইডটা, আর ওইটা থ্রু বেস কালেক্টরে চলে যাচ্ছে ফর্মিং দ্য কালেক্টর কারেন্ট। তাহলে যখন তোমার ইনজেকশনটা নেই, তুমি কোনো বায়াস দিচ্ছই না, তখন তো এই পার্টটা অ্যাবসেন্ট আছে, শুধু থার্মালি জেনারেটেড ক্যারিয়ার্স যারা রিভার্স বায়াস জাংশনের জন্য সেপারেটেড, ড্রিফটেড এন্ড সেপারেটেড গিভস দিস কম্পোনেন্ট। তাহলে যখন আমি লাইট দিচ্ছি, লাইট ফলস অন দিস রিভার্স বায়াস জাংশন, তখন photo generated carriers will behave like the thermally generated carriers, আর অরিজিন থার্মাল এনার্জি কার লাইট দ্যাট ডাজ নট ম্যাটার, ওরাও এখানে জেনারেটেড হয়েছে, এবং in this depletion region they are being separated and give rise to the current। তাহলে আমার এই বায়াসের অ্যাবসেন্সে যখন ক্যারিয়ার ইনজেকশন নেই, তখন দিস ওয়াজ দ্য অনলি কম্পোনেন্ট, এইটা ডিউ টু থার্মাল জেনারেশন। এবার যদি আমার লাইট পড়ে, ওর সিমিলারলি যেভাবে থার্মাল এনার্জির জন্য জাংশনে কেরিয়ার ইলেকট্রন হোল পেয়ার জেনারেটেড হলো, এবার অপটিক্যাল এনার্জি রেডিয়েশনের জন্য সেটা হলো। কাজেই তারা কিন্তু এই একইভাবে ট্রিটেড হবে। কাজেই এই আইসিইউ ও যেটা ছিল সেটা বেসিক্যালি এখানে আমার আইপি ফটো কারেন্টটাও যোগ হচ্ছে।
ম্যাম,
হ্যাঁ,
ওই অ্যাডমিট করার জন্য বলছিল কিছু ছেলে।
ও, এরা ক্যান্সার এতগুলো ওয়েট করছে না। কালকে তোমাদের প্রোগ্রাম দেখে আমি তো বেশ স্কেয়ার্ড। ফোন নিয়ে খেলছো আর হ্যাঁ ম্যাডাম, হ্যাঁ স্যার, বুঝেছো, ইয়েস ম্যাডাম, ওদিকে তাকিয়ে আছে তো ফোনের দিকে। কি যে তোমরা করো সত্যি। আচ্ছা, ইয়ে কিছু ক্লিয়ার হলো কুশল?
ম্যাম মোটামুটি হয়েছে, পুরোটা ক্লিয়ার
আচ্ছা,
হয়নি।
হ্যাঁ, এই ট্রানজিস্টারটা আজকে পড়াই। ট্রানজিস্টার পড়ানোর পর যদি মনে করো যে ওটা ক্লিয়ার হয়নি আমাকে একটু মনে করে দিও, তখন আবার এসে ফটো ট্রানজিস্টারটা ডিসকাস করবো, কেমন? তাহলে আমি ক্লাস শুরু করি 10:03। এক্ষুনি আবার এসে রিকোয়েস্ট করবে। এখন
আরেকটা ম্যাম ডাউট ছিল,
হ্যাঁ,
আরেকটা ডাউট ছিল
কিসে?
ম্যাম। ওই সোলার সেলে যখন করা হচ্ছে
হুম,
ম্যাম, তখন তো সার্কিটে কোনো কারেন্টই ফ্লো করা উচিত না
হুম।
ম্যাম। তাহলে ওই ইকুয়েশনের মানে আমি বলছি যে আইপি আইএফ এই কোনো টার্মই তো থাকা উচিত নয়, আমরা জাস্ট আই ইকুয়ালস টু জিরো করছি।
I is
কারণ
the
কমপ্লিট
current that flows through the external circuit. আইটা আমার এক্সটার্নাল সার্কিটে যে কারেন্টটা হওয়া উচিত। এবার আমি যদি লোডটা ইনফাইনাইট মানে ওপেন রাখি, তাহলে তখন আর তোমার আইটা জিরো, নেট কারেন্ট ফ্লোয়িং থ্রু দ্য ডিভাইস জিরো হবে। মানে ইন্টারনালি যেটা তোমার ফটো কারেন্ট, সেটা তো মানে কেরিয়ার জেনারেশনটা তো আছে, যার জন্য ভিওসি হচ্ছে। তুমি বলছো ওপেন মানে কোনো কারেন্ট নেই, তাহলে আইপি আইএফ কিছুই হবে না, তাই তো?
হ্যাঁ ম্যাম, এটাই বলছি, মানে সব কারেন্ট কম্পোনেন্ট জিরো হয়ে যাবে
সব
যেহেতু
কারেন্ট
ওপেন সার্কিট আছে।
জিরো, হ্যাঁ, সেটা তুমি ওপেন
মানে
সার্কিট।
আমি বলছি যে ওপেন সার্কিট ভোল্টেজ শুধু ইনক্রিজ করবে।
হুম,
হ্যাঁ
হ্যাঁ, কিন্তু সেইটা তোমার ইন্টেন্সিটি, ইনসিডেন্ট রেডিয়েশনের ইন্টেন্সিটির সঙ্গে তোমার আইপিটা ডিপেন্ড করে। সেই জন্য আমি এক্সটার্নাল সার্কিটে জিরো করে দিলাম, কোনো কারেন্ট নেই, তাহলে ওকে আমি ইনসিডেন্ট রেডিয়েশনের ইন্টেন্সিটির সঙ্গে রিলেশনটা বার করতে পারছি। কনভিন্স নাও, বুঝতে পারছি। আচ্ছা, এবার আমি শুরু করি, আর আমি অ্যাডমিট করতে পারবো। দেখো এখানে কিন্তু তোমার আইএফ নেই, আইপি আছে, I0 আছে। I0 মানে তোমার রিভার্স স্যাচুরেশন কারেন্টটা, তাই তো, থার্মালি জেনারেটেড কেরিয়ার এটা রইলো। আর আইপি হচ্ছে তোমার ইনসিডেন্ট রেডিয়েশনের জন্য যে কম্পোনেন্টটা হতে পারে। কারণ এইখানে যে কেরিয়ার গুলো জেনারেটেড হচ্ছে তারা সেপারেটেড হচ্ছে, তাদের জন্যই ভিওসিটা ফর্ম করলো, এটাও ঠিক। আবার ওদের দিয়ে মানে আমি ভিওসিটাকে আমরা চাইছি টু এক্সপ্রেস ইন টার্মস অফ incident radiation intensity. IP is basically measure of that intensity. IF তো নেই এখানে, আর এটা তো থার্মালি জেনারেটেড কেরিয়ার, রেডিয়েশন অলরেডি আছে, থার্মালি জেনারেটেড কেরিয়ারও আছে। তুমি বলছো তারা কারেন্ট ফ্লো তো দিতে পারছে না ওপেন বলে, সেইটা আমার এক্সটার্নাল সার্কিটে, কিন্তু কেরিয়ার গুলো তো ফ্লো করে এখানে আর এখানে জমা হচ্ছে, that will give rise to your open circuit voltage. কটা বাজে? 10:07। এবার আমি শুরু করি। আর কেউ ওয়েট করছে? করছে না। LCD, liquid crystal display, and it is a passive device. No energy conversion takes place here, so it is a passive device. It functions as a display device by controlling the transmission and reflection of light through this cell. So liquid crystal, LCD, liquid crystal display. So what is liquid crystal? It is basically an organic liquid, and where its molecules are long rod-shaped molecule. So the general tendency of these molecules are that they always align parallel to each other. So say some regular arrangement is maintained all through the material, and thus it is called a crystal, just due to that arrangement of their molecules. It is called a crystal, and as it is a liquid one, it has the flexibility of liquid, and we can, in general, the long molecules are aligned parallel to each other, but by applying some external field or anything, we can disturb their alignment. And accordingly, the properties, it will exhibit optical properties that is influenced by the applied electric field. So such ordering in molecular arrangement, there can be 3 types of ordering: nematic ordering, cholesteric ordering, and smectic ordering. In between this one, the nematic ordering is the most common one, and so nematic liquid crystals are most popular. Now, structure of LCD. Basically, the liquid crystal is confined within a pair of plates, one of which, at least one of these plates should be transparent. So between these 2 glass plates, the liquid crystal is confined, and the outer surface of these 2 glass plates, there will be some transparent conductor, film of transparent conductors are deposited. So this coating of conducting material will allow us to apply some electric field. They will behave as the electrodes. So we can apply an external field across this two plate. Conducting material, as already discussed in case of solar cell, we have seen that indium SNO2 or IN2O3, they are the transparent conductor. Now, separation between these two plate is roughly 10 micron. The gap between this 10 micron gap is filled with liquid crystal. Now, liquid crystal, sometimes it can be used in to work in transmissive mode or reflective mode. When it is used in transmissive mode, a light source behind the plate is required so that light can transmit through this unit and appear to the viewer. Whereas in reflective mode, light source must be on the same side of the viewer. So light will pass through this. On the back of this plate, there must be some reflective coating, and it will be, the light will be reflected back and come to the observer. So it can be operated in different mode. The most common LCD is the twisted nematic type. In nematic ordering, molecules tend to align parallel to each other. The orientation of molecules is represented by a vector called director. So the direction along which all the molecules are naturally aligned band will be wider. Now we can fix this director according to our need. So the director can be fixed by a grooved surface in contact with the liquid crystal. That means these are the inner side. These are the two plates. A groove, vertical groove is etched on the inner surface of this plate, and on the other plate, on the inner surface, that means the surface which is in contact with these molecules, our horizontal groove is etched. So what we'll do for normal purpose, normal condition, these long molecules will occupy such groups and will be fixed. Our features is inside by this. In this group, they will be attached in this group and fixed. They cannot move. So here, as one molecule is fixed in the groove, means its orientation is like this, the adjacent molecules will also be aligned like this, parallel to this one. On the other hand, to the opposite face, this is an horizontal groove, so some molecule will be, some molecules will occupy this position attached to this groove, and the neighboring molecules will try to
পয়েন্ট চিনতে
align
থাকবে
like this on horizontal.
তো ওটা কি লিখতে হবে?
That means since it is a liquid, it has that flexibility. On the two extreme side, molecules will follow this direction of this groove, and in between, they will gradually consume this 90-degree rotation. Slightly bend, rotate korte korte. So these 90-degree change in their orientation will be gradually consumed over this distance, 10 micrometer. Okay. So when the liquid crystal is operated, then there will be the outside, there will be a pair of polarizer plate, cross polarizer plate. So one plate at this side, this is the input side from which the light will incident. So there will be vertically polarizing plate, and on the opposite side, there will be horizontal polarizer. So when light incidents on it, light enters the medium, they will also undergo this 90-degree rotation while passing through this space between two plates. As the molecules of the material undergoes gradually consumes this 90-degree rotation, so does the incident light. And a vertically polarized light will enter only through this plate. they will gradually undergo 90-degree change and will come out through the horizontal polarizer. And light will be transmitted through this. But in presence of applied electric field, if we apply some electric field across this plate, all the molecules of the will follow the direction of the electric field, will be aligned along the direction of electric field. Now, only these molecules which are in contact, which is confined in the groove, cannot move. But in between, all the molecules will now follow the direction of the electric field. If electric field is applied in this direction. So, now what will happen when we apply some electric field? Then molecular arrangement is like that, and the incident light comes, the vertically polarized light comes out of this plate and undergoes abrupt change in 90 degrees. So the light cannot follow this orientation, and obviously it will be blocked by the horizontal polarizer, and no light will come out of the cell. So the material will appear dark. So this is the basic operation of a LCD, twisted nematic cell.
ম্যাম
আচ্ছা, কি ওয়েট করছে কেউ?
মিস একজন বলছিল অ্যাডমিট করতে, কিন্তু তারপর সে আছে কিনা এখন আমি জানি না।
আর হবে, আর কাউকে নেব না। বলো বলো, কে কি বলছিলে?
হ্যাঁ, আমি বলছিলাম যে সেকেন্ডটা তো বুঝলাম যে ওটা হচ্ছে কি যেখানে ডার্ক দেখানোর কথা সেখানে ওরকম করা হচ্ছে, কিন্তু যেখানে লাইট পড়ার কথা সেখানে ওরকম ভাবে পোলারাইজ করে মানে লাভটা কি হচ্ছে তাতে? এত কিছু যে করলে তাতে লাভটা কি হবে?
বুঝলাম না। তোমার লাইট পাস করে চলে যাচ্ছে, ট্রান্সপারেন্ট।
সেটা তো এমনিতে ট্রান্সপারেন্ট থাকলে তো এমনিতে পাস করতো।
বুঝতে পারলাম না, আরেকবার বলো।
ম্যাম সে তো এমনিতে একটা ট্রান্সপারেন্ট গ্লাস বসিয়ে তো হয়ে যেত, এত কিছু মানে অর্গানিক মেটেরিয়াল দেওয়ার দরকারটা কি ছিল?
না না, তুমি কন্ট্রোল করলে তার অ্যাপিয়ারেন্সটা। এইবার তোমার দেখো, এইটাও যদি আমি 7 সেগমেন্ট ডিসপ্লের মতন, আমার 7টা সেগমেন্টের জন্য 7টা এলসিডি দিয়ে রেখেছি। এইবার আমি 1 ডিসপ্লে করব, তাহলে আমাকে ওই দুটো সেগমেন্টে আমাকে বায়াস দিতে হবে। So we apply the bias. In case of LED, those segments glow. In case of LCD, আমার যদি যেই সেগমেন্টে আমি ইলেকট্রিক ফিল্ডটা অ্যাপ্লাই করব, ধরো বায়াসেরই মতন ব্যাপারটা, তাহলে কি হবে, সেই সেগমেন্ট গুলো ডার্ক অ্যাপিয়ার করবে। So you can see the 1 digit. সেটাকে তুমি এমনি গ্লাসে পাততে? তুমি তো ডিরেক্টরটাকে কন্ট্রোল করে এই জিনিসটা করছো।
আচ্ছা,
ক্লিয়ার? আমি বুঝতে পারলাম না।
ঠিক আছে।
We are controlling the property of the crystal, liquid crystal. কোনো এনার্জি কনভার্সন হচ্ছে না। একটা এক্সিস্টিং লাইট সোর্স will be blocked when we apply some field, otherwise it will pass through this. তাহলে এই যে প্রপার্টিটা চেঞ্জ হলো লিকুইড ক্রিস্টাল ইন প্রেজেন্স অফ লাইট, সেটাই আমাদের উদ্দেশ্য ছিল। We control the light passing through this one. এটা another type of liquid crystal, অত আমাদের দরকার নেই, যেটা মেকানিজম অফ ডাইনামিক স্ক্যাটারিং করে। সো ছেড়ে দাও, ওটাও তোমার দরকার নেই। দেন অ্যাডভান্টেজ: low power, low cost, slim profile, lightweight. Application watches, clocks, calculator, portable computer monitor, ছেড়ে দাও সব, automotive dashboard, etc. etc. এটার ডিসঅ্যাডভান্টেজ কি? ইট ইজ স্লোয়ার দেন আওয়ার LED. 100 to 300 মিলিসেকেন্ড ইটস সুইচিং স্পিড। মানে তুমি অ্যাপ্লাই করলে, উই অ্যাপ্লাই দ্য ফিল্ড, it will follow the behavior according to the depending on the electric field, but there will be this amount of delay. But for most application, this is not a problem because we do not use this as source, light source, because there is no light conversion of energy. So for only display purpose, that will not matter. Why it is slower than LED? LED is slow because injected carriers will have to diffuse and again will recombine and only then light will appear. So some finite time, recombination lifetime, finite time is required. That makes the device bit slow. But here in case of LCD, it is slower because now the long molecules, organic molecules will have to reorient it. They will follow some orientation, and as the molecules are quite large, so their inertia will make the response slower. So this is the liquid crystal display. So another two small units, 7-segment display. It is already discussed in lab, during lab class. Should I explain again it? Is it clear to all or should I explain? That means clear. Clear na hole bolo. So common anode type and common cathode type. There will be, these are the configuration, internal configuration of this, and there are the 7 segments. So advantage of
ম্যাম আমরা মানে প্র্যাকটিক্যালে যে ডায়াগ্রামটা ছিল ওই 7টা সেগমেন্ট আঁকানো ডায়োড দিয়ে, তো ওটা বুঝতে পেরেছি, বাট এই পাশের ডায়াগ্রামটা একটু বুঝিয়ে দেবেন?
এগুলো
এই যে মানে কোনায় যেটা ডায়াগ্রামটা আছে
এইটা,
হ্যাঁ
না না, এটা 7 সেগমেন্ট ডিসপ্লে না, এটা হচ্ছে আলফা নিউমেরিক ডিসপ্লে। আমি 7 সেগমেন্টটা বলছি। দিস ইজ দ্য 7 সেগমেন্টস করেসপন্ডিং টু 7 এলইডি। দে আর
কমন অ্যানোডটা করেছি, আপনি একটু কমন ক্যাথোডটা করে দিতে পারবে?
কেন নয়, তাহলে কি ছবিটা আঁকবো? দেখো
ডিফারেন্সটা বুঝতে সুবিধা হতো।
হ্যাঁ হ্যাঁ নিশ্চয়ই। কমন অ্যানোড মিন্স our purpose is we will use 7 LED for 7 segments. So to display some digits or some symbol, whatever we need, we will have to provide forward bias to selected segments. So if we want to display 1, decimal 1, then this B and C, 2 LEDs which represent these 2 segments should be forward biased. Then these LEDs will glow and we will get the display of 1 like this. So now for these 7 segments, 7 LEDs are there. Now these 7 LED will have 7 into 2, 14 terminal. To forward bias this 7 LED, we should use these 14 terminals. But to make the circuit less cumbersome, what we do? Basically, either the 7 anodes of all these 7 LEDs are shorted like this, and only 1 terminal is taken out from this. And the cathode of all 7 LEDs are open, independent. They can be used independently. Now, this is the common anode configuration. All LEDs are shorted internally, so a single terminal is there. That means in place of 14 terminals, now we will have to handle 7 cathode and 1 anode. So 8 terminals only. Now we connect a positive supply through a current limiting resistor, obviously, to the common anode. So all 7 LEDs now get for positive voltage at their anode. Now their cathodes are open. Now if we selectively, the negative terminal of the battery, which we are calling the ground one, this one is the floating one. Now if we connect this ground to this LED, cathode of this LED, then only this, it has already get the positive voltage at the anode. Now as soon as we connect the ground of the supply to this cathode of this diode, this LED will get forward bias and it starts glowing. For others, their circuit is not complete. They are not getting forward bias because their cathodes are not connected to ground. So even if the positive terminal is connected, the circuit is not at all complete for other LEDs. So they will not glow. So this is common anode configuration. So first we apply this cathode to each of these terminals separately and identify which number of pin corresponds to which segments. Once this pin configuration of 7-segment display is known, then we can selectively choose the terminals and we'll connect this ground terminal to those cathodes so that selected LEDs glow. Okay. Now there's another possibility is again all cathodes, 7 cathodes are shorted internally and we take out only a single terminal which is to be permanently connected to the negative terminal of the battery. That means now all 7 LEDs get negative voltage at their cathode. Now their 7 LED anodes are now open and the positive terminal of the battery will be connected to a current limiting resistor and now this terminal is free, open. Now as soon as we connect this to the anode of particular LED, that LED will get the complete forward bias and will glow. And others will not. So similarly, for common cathode configuration, we can thus identify which pin, which LED corresponds to which segment. And in similar way, we can display any desired digit. So for common cathode means 7 cathodes are shorted and we take out only 1 cathode and we make it grounded, connected to the negative terminal of the battery. And now anodes are free. So we'll have to apply the positive bias to anode of selected LED. Clear? Now, by this 7-segment display, all decimal digits can be displayed, but limited alphabet and symbols can be displayed by this 7 segments. That is the inherent disadvantage of a 7-segment display. So to overcome this problem, we consider alphanumeric display. Alphabet and numerics, all digits can be displayed by this. So the name alphanumeric display. So we call it dot matrix. So there is a large array of LED is taken. So it is a common one, 5x7 LED. 5x7 LED matrix. So in this large array, in case of 7-segment display, each LED will appear as a segment. Whereas here in this large array, each LED will appear as a dot. So as each LED appears as a dot, there is the flexibility. We can display any symbols, digits, alphabets by using this dot matrix because they appear as a dot in the large assembly of LED. So basically these LEDs are displayed, are connected like this, 5x7. So 5 columns and 7 rows in this array. And LEDs are connected by these are the electrical connections, shorted. These cross points are not connected. These points shows that there are electrical connections is established in these points. So now say this one, for a column, there are such 7 LEDs. And all these LEDs have their anode shorted to this column. And their cathodes are connected to a particular row. So if we short this one, say we want 3x2 LED. So each one can be identified by their position in this matrix. So if we want that our 3x2 LED should glow, then there will be 3 means 1, 2, 3, third column, and 2 means second row. So this second row and third column switch will be shorted. Then the plus V voltage will appear at the anode of all 7 LEDs. But at the cathode of only this LEDs, when it is shorted, ground appears at cathode of all 5 LEDs. But only this LED, 3/2, this LED gets positive voltage at its anode and 0 at its cathode. So it gets the forward bias and it will glow. So larger matrices are available. They available in a chip, and thus we can selectively apply forward bias to specific LEDs. And this, as they appear as dot in this large assembly, there is the flexibility, and we can display any field, symbol, alphabet, digits, etc. So optoelectronic portion is covered. Now we will consider BJT. BJT তোমরা 12 এ পড়েছো, আইডিয়া তো আছে নিশ্চয়ই। ও রেকর্ড করা হয়নি তো, BJT-টা করি। খুঁজে পাই না কেন, যেটা ওপেন থাকে সেটা। BJT-র নোট কি তোমাদের দিয়েছে?
না ম্যাম।
ওকে, ক্লাসের পর দিয়ে দেবো। So BJT, bipolar junction transistor, or simply bipolar transistor. Why you call bipolar? Because carriers of both polarities play active role in operation of such 3-terminal device. So it was discovered in 1947 by Bardeen, Breton, and Shockley, and due to discovery of this, the revolution in semiconductor technology started. It is a minority carrier device with 3 terminals. Emitter, the terminal emitter, it emits carriers. Base, the common thin layer between input and output, between emitter and collector. And collector, it collects the carriers injected by the emitter base junction. So emitter emits carriers and collector collects those carriers. And those emitted carriers must pass through the intermediate layer, which is called base. So there are 3 terminals, emitter, base, and collector. This is the structure. This was the substrate, N-type silicon. So over this N plus silicon substrate, epitaxial layer is grown of light doping. তোমার তো fabrication related কিছু এখন কোনো exposure নেই, because this epitaxially grown, because if we want to form a less N-type layer over this heavily doped N plus, it is not possible. So we use epitaxial layer. Whatever, this is a lightly doped N region that forms the collector. These 2 forms the collector. There is a complete surface is covered with thin metal layer, and this metal contact we take the collector terminal from this surface. Then within this N region, P region is formed by diffusion, and within that P, again, another heavily doped N plus region is formed. So metal connections are taken out from these two regions. So this forms the emitter, and this forms the base, and this one the collector. So basically transistor is manufactured by this repeated diffusion. So by compensation doping, this N-type collector has been made P-type. Again, that P-type has been converted to heavily N. So the compensation doping makes this type of structure feasible. Now, if we consider this section, this two section, the region between two vertical dotted line, and we use it, draw it like this. So this portion is the emitter layer, then this thin portion is the base layer, and this one, the larger one, again gives the collector. So this, we take out the slice of this device from this region, and we get this configuration: emitter, base, collector. Emitter is heavily N, this is P, and collector is N. So this is our transistor. So we will discuss now how a transistor works. So I is positive when it enters, current enters through the terminal, then current will be taken as positive. And when the voltage, the applied potential or voltage will appear as positive when the terminal is at higher potential. So these are our convention. Now we will discuss how a transistor can work. For normal operation, or for normal working, the emitter base junction should be forward biased, so that we know that under a forward bias, the carrier injection takes place. So emitter base junctions are forward biased and collector base junctions are reverse biased. This is the normal working condition of a BJT. So accordingly, as we have considered the NPN transistor, we take this VEE, supply voltage. When it means supply voltage, this subscript will be repeated. So on the emitter side, this is the supply voltage, VEE. So the negative of this should be connected to N plus emitter and positive to the common base. Then the N plus P junction will get forward bias. It is not the practical circuit. We did not connect the current limiting resistance, which must be there for original circuit. Here we are only interested in how the BJT works. So we did not connect this resistance. On the output side, this is VCC, supply voltage connected in the collector side. So it should be reverse bias. N-type collector should be connected to positive terminal of the supply and the negative one to the base. And thus, base is common between these two one. Now, these are the different carrier flow. Now, as emitter base junction is forward biased, then carrier injection will take place across this interface. So electron will be injected into P-type base and holes will be injected into N-type emitter. But we have made it heavily doped, N plus P junction, so that carrier injection, strong carrier injection will take place from emitter to base with respect to the hole injection from base to emitter. So shaded ones represent hole flow and this one represents electron flow. So due to this forward biasing, large electrons are injected into the base. Now here in this base region, at these two junction, there will be depletion region, since it is forward biased, depletion region will be very thin, will not consider this depletion region, but collector base junction is reverse bias, so depletion region will be wider in this region. Now what will happen? At the edge of the depletion region within the base, carrier concentration is 0 as it is depletion region. Whereas, so electron concentration at this edge of this depletion region is 0, whereas large number of electrons has been injected in this side. Now, ছবি না দেখালে হবে না। শুরু হলো। So these are the depletion region. I draw the depletion region wider on the collector side because we have converted the p-type base. We have converted the n-type collector into p-type base by compensation doping. So the concentration of impurity in the p region must be higher than n-type collector. আপত্তি থাকলে, if you do not accept this, tell me. So this is the depletion region. So N side means the depletion region here is positive, ionized donors. বলো কেউ কিছু বলছিলে?
কালেক্টর সাইডে ডিপ্লেশন রিজিয়নটা একটু ওয়াইড কেন?
ওয়াইডার কেন? এই যে আমি বললাম যে we will start on the over the wafer substrate, and n-type region is formed. That forms the collector. Then we diffuse p-type base into this n region. Form the structure টা দেখো একবার। পাই না কেন এখানে এগুলো? ও আচ্ছা, এটাকে মিনিমাইজ করি। Look at this structure. So over the substrate, n plus substrate, the epi layer, n-type epi layer is this one. The epi layer is grown. Then we, through these photolithographic procedures, etc., we have opened a window and acceptor atoms are introduced into this n minus n layer, collector layer. So if your acceptor concentration is much greater than the donor concentration in n-type collector, then a region will be formed like this. P region is formed within this collector, and again from another window selectively this region is made heavily n. That means we have converted a n-type region to p-type. So if its donor concentration and acceptor concentration of these two regions equal, then the material will have no type of carrier will dominate. So to make it p-type, our Na must be much greater than this, so that Na minus Nd for collector and Na is for base, Na minus Nd is much greater than our intrinsic carrier concentration according to compensation doping. So to make this p-type base, we must have to introduce acceptors much higher than the donors in the n-type collector. We always call that base should be very lightly doped, but we do not tell that it is more, but it is obvious that it should be lightly doped, but doping should be lighter in that case. So collector doping is always smaller than this base. So for the reverse bias base collector junction here, the depletion region will extend more into the collector region than into the base. And this is the N plus P junction. So we are not considering the depletion region of this because this junction is forward biased. Is it clear? কে জিজ্ঞেস করলে?
Yes, ma'am.
So we will see that this is the original base, the metallurgical junction, distance between these two metallurgical junctions. This is our original base width. These two separation between these two interface, and that is called say WB. That is the original base width, but effectively the base width of this neutral base region is less than this due to the presence of reverse bias applied across the collector base junction. So depletion region extends on either side of the layer, base and collector. But since our collector is quite wide, so we do not bother about this one. We are interested in base region because base itself is quite thin, and depletion region, due to extension of depletion region within this material, effective neutral base width is only this one. Now, what happens when the electrons are being injected from N plus? Sorry, it should be heavily doped. N plus. So when electrons are injected from this to this side, say লেখার উপায় নেই। There will be large number of carriers. জায়গা রাখিনি। So this is the edge of the depletion region within the base, this one. So here carrier concentration is 0 because within the depletion region carrier concentration is 0. So here electron concentration is 0, and from N forward biased N plus P junction, large number of electrons has been injected within this. So this is the electron concentration at the interface, and this is 0 here. So within this there will be some concentration gradient, and injected electrons from emitter side will diffuse through the base. From moving from this point to this point, they will diffuse and will recombine. Okay, so this will be the profile. I will come to this point later, and then thus the electrons will diffuse to this and will diffuse through the neutral base and will reach the edge of the depletion. Then they will be swept by the junction field. Junction field is in these directions: positive space charge and inside collector and negative on the base. So junction field is in this direction. So once the injected electrons from emitter diffuses through the neutral base and reaches the depletion region, they will be subjected to the field in this direction and will be readily swept through the depletion region and will appear on the collector side. And here, due to this bias, positive terminal of the battery is connected to the collector. So, positive terminal of the battery is connected to the collector. So, these electrons, once enter the collector, will be collected by the supply due to the polarity of the supply. Thus, the area electrons injected from emitter will reach the collector and produce the collector current. Is it clear?
ম্যাম
So, বলো।
ম্যাম এমিটার আর বেসের মধ্যে যে জাংশনটা হচ্ছে ওখানেও তো একটা ডিপ্লেশন রিজিয়ন হবে, যেটা এমিটার সাইডে অনেকটা লেস হবে ডিউ টু এন প্লাস, আর বেস সাইডেও তো একটা
But we will ignore that because since N plus itself is heavily doped and because of it is this junction is forward biased. Depletion region will be very thin. So we are not considering the extension of the depletion region within neutral base. Basically, that is ignored compared to this region. Okay. We consider only this collector base junction, depletion region in the collector base junction. Because that is reverse bias, you will be lost. So we ignore the existence of depletion region in forward bias junction. So from emitter, electrons are injected within the neutral base, they diffuse over the neutral base, reaches the depletion region, the junction field swept them and bring them on the inside collector, and due to the external bias, they will be collected efficient. So that will constrain the collector. Now, this how efficiently the injected carriers from emitter reaches the collector and being recorded as the collector current, that will determine the quality of the BJT. Now we are considering only the carriers injected from the emitter. But again, as we forward bias this emitter based junction N plus P, then some hole will also be injected in the opposite side. We make this N region deliberately heavily doped so that, and this is our lightly doped, so that the whole injection from base to emitter becomes quite weak. Our purpose is we will inject carriers from emitter and we will collect them from collector. So this component of carrier injected emitter injection from emitter to base is the important component we are interested in, but we cannot ignore them. There will be always some hole injection in the opposite side. So this electron injection from N plus to P so this injection of electron from emitter to base, and which there will be always some hole injection from base to emitter. So total emitter current direction will be from base to emitter because electron flow in this direction means current direction is opposite. So total emitter current IE will have two components. IEN, component of emitter current due to electron injection, and IEP, component of emitter current due to hole injection. So our IE will be IN plus IP. Okay. And we will always, this component will not contribute to our collector current. So smaller this component, better is the transistor. So we will always try to keep this very small compared to this one. And we define in emitters, emitter emitter injection efficiency as IN by IN plus IP. So it is the ratio of this electron component of emitter current by the total emitter current. So how efficiently it is injecting the desired type of carriers, that is the measure of emitter injection efficiency. IEN, the desired component by the total emitter. So we will keep it very small. Sorry, this term will be kept very small so that this ratio is more or less close to 1. This gives the main configuration. So it is nearly 1 but always less than 1 because we cannot make it. However, lighter doping we use for this base, it will, if it is very lightly doped, still there will be a component. Now, another point, when the electron, injected electron enters in the p-type base, it will diffuse across the neutral base. Now, during its passage through this, transit through this, it is p-type material. So, majority carriers are whole. So, injected electrons will recombine with the holes in the p-type base. So part of injected electron will be lost due to recombination and the rest will appear in the collector and forms our desired collector. So again, we will try to make this recombination as small as possible. So that again the requirement is p-type base should be very lightly doped. I will come into this point later. Now for the time being, there is the injected electrons entering through the base. A small portion of electron recombines with holes in this p-type base and the rest moves this one. So our IC basically comes from IEN, but a small portion of IEN is lost here. So IC is again always small than our IE, but if we can minimize, keep it very small, then IC is roughly equal to I. It is always less than I, but is more or less as the same value. IC is roughly equal to I. IEN rather. Now, what will happen? This they will recombine. When this injected excess carriers recombine with the holes, few holes in the base, so some space charge will be developed there. Few holes are lost. Initially, it was electrically neutral, equal number of acceptor ion and equal number of free hole. Now, few hole has recombined with injected electrons. That means few ionized acceptors now will be there that will make this region slightly negative due to the negative space charge. Now, as this process continues, as this injection continues, more and more holes are being recombined. So gradually this layer will develop some negative charge. And the p region negative means its effect forward bias will be less. So carrier injection will be weaker and the process continues and ultimately carrier injection will stop in absence of this bias. But we apply some DC voltage across this so that the holes lost from this neutral base region due to recombination will be resupplied onto that. Class নিচ্ছি পরে কথা হুম হুম so this lost
ম্যাম
holes হ্যাঁ
ম্যাম বলছি ওটা কিভাবে রিসাপ্লাই হচ্ছে?
we are connected it to DC source DC supply এখান থেকে ইলেকট্রন যাচ্ছে আর এখান থেকে হোল ঢুকছে
ওকে ম্যাম
so this supply will this power supply will supply the holes lost due to recombination. So there are two sources. the supply will have to supply holes, the battery will have to supply holes lost in two different ways. One is some holes are being injected from p base to electron, n-type electron, and some holes are being recombined with injected carrier. So these two component of hole which is lost, should be compensated by the battery to maintain the steady state. We are applying this battery means the system is now should be in steady state. It has come out of equilibrium. So this electron injection will be maintained by this battery, and this will also maintain the true source of loss of holes during this operation. So electrons injected from within the base will lost, small part of it will be lost due to recombination, and rest reaches the collector to yield collector current. And from this battery, whole supply will be maintained so that this loss of electron, this component of hole, will be resupplied, and the whole component which is being injected into the N emitter. So this is the whole flow associated with this. So these are different carrier flow, and correspondingly we get this current. So this IN, N component of emitter current, electron component of emitter current, that is IN in this direction because this is electron, and IEP, whole flow in this direction will give IP. So sum of these two will give IE, emitter current. So for NPN transistor, the current coming out of the emitter terminal, out through the emitter terminal. So IE is negative according to our convention. When current enters to the terminal, it is positive. So this IE is negative. Now, what are the other component? This one, ICN, electron flow from this. That means this ICN direction will be this one, opposite. So the collector current enters to the collector. So it is positive for NPN transistor. What about base? Through this base terminal, this whole holes will be supplied. So our base current will also be positive because holes enter through this terminal into the device base. So base current is also positive. So IE is always IC plus IP. Because this is the injected carriers, then these are the loss. IB will compensate the loss of electron while passing through the base, and IC is the output current. So IE is IC plus IB. Now, if in absence of this one, say this battery is not connected, then there will be no carrier injection across this N plus P junction, and we cannot expect any carrier here. So IC is also 0. IE 0, IC 0, but some component will also still be there, which is this two, small one. It is a reverse bias junction at finite temperature. There will be thermally generated carriers, and those thermally generated electron and hole will flow in this direction. Minority carriers, the thermally generated electrons in p-type base will move in this direction by the junction field and enter the N region. Similarly, minority holes in N collector adjacent to the depletion region will enter the junction region and will be swept to the P side. So this IC0, ICE0 is formed. Electron flow in this direction, that means current is in this direction from N to P, collector to base. So that is ICEO. That means ICEO কেন বলবো, এটা তো আমি কমন এমিটার বা কিছু বলিনি। আচ্ছা আমি এটা দেখতে পরে ICE or ICB, whatever, there will be some non-zero component of current in absence of carrier injection from emitter. That is only due to thermally generated carriers. So net IC will be this ICL plus this leakage component. We call it leakage component because that is due to the thermal energy. That is not electrically controlled. So it is behave as an leakage component. It is not a desirable component. আচ্ছা এই সবগুলো এখন বলবো আপাতত for the time being how a transistor works. Is it clear? Should I repeat or should I explain any part again? These are the basic carrier flow and current component that takes place in a BJT. So I am assuming that it is clear to you. Follow.
ম্যাম যদি ভিসিসি ইকুয়ালস টু 0 করে দেওয়া হয় তাহলে আমি বলছি
VCC?
নো বাই হ্যাঁ
হুম
ম্যাম তাহলে ওই বেস থেকে কালেক্টরে একটা মানে কারেন্ট কম্পোনেন্ট তো আসবে ডিউ টু বিল্ট ইন ইলেকট্রিক ফিল্ড ম্যাম সেটার জন্য কি আইসিইওটা আসছে
V is already 0. It is withdrawn. If you also withdraw this, then there is no bias. So the system is in equilibrium. So due to thermal
না
energy,
ম্যাম
হ্যাঁ
আমি বলছি ভিইটা আছে মানে
এটা আছে
এমিটার হ্যাঁ
এটা
তারপরে
নেই
আমি হ্যাঁ
তাহলে তো কাজ হবে না তোমার injected electron can reach here only. If your V is there, this injection will take place. Injected carrier will reach the edge of the oh, there is no reverse bias, so there will not be depletion region will also not be there. So the injected electrons will enter the p-type base and these entire carriers will recombine with base and that will be resupplied by the battery. So it ends within this only, this single junction. It is not reverse bias.
বিল্ট ইন ইলেকট্রিক ফিল্ডের জন্য কিছু হবে না
এখানে
হ্যাঁ ম্যাম
বিল্ট ইন ইলেকট্রিক ফিল্ডের জন্য কি হবে বলো এই যে তার মানে কি তুমি এই জাংশনটা তো ইউ ডিড নট বায়াস দিস জাংশন না
হ্যাঁ ম্যাম
rather you will see that in absence of this you have this is present still. That means p type base is getting positive voltage and c does not get anything, so your base collector junction is also forward bias. তাই না
ও
So
আচ্ছা
some
ম্যাম হ্যাঁ
এখানে বায়াসটাই নেই উল্টে এই সাইডটা তোমার পজিটিভ তার মানে এখান থেকে কিছু হোল ওদিকে ইনজেক্টেড হলো হয়ে the wide neutral end region they will recombine and will be lost. Electron তো in any case ওদিকে যাচ্ছে না. So we must bias this. For transistor operation, this for input junction, base emitter junction should be reverse forward biased, collector base junction should be reverse biased. Should I proceed? So for PNP transistor, direction of current and polarity of different voltages will be opposite. Here, the BJT, since it has 3 terminal, we can use it in 3 possible configuration. So I am talking in terms of NPN transistor. So common emitter configuration. Common emitter means out of this 3 terminal, emitter is taken common to both input and output. So emitter is the common terminal. So base will be the input terminal and collector the output terminal. So since it is NPN, that means electrons being injected, so current is coming out through the emitter terminal. So in the symbol, we put this arrowhead on emitter. So this implies this is arrowhead, the terminal with arrowhead is always emitter, and it coming out means it is NPN transistor. And base, through the base, whole serving supplied. So base current is entering through this base terminal, and electrons are coming out through collector, means collector current direction is also entering to collector. So IB and IC are positive, and the input voltage base with respect to common terminal, VBE. The second subscript is always the common one. With respect to this, the potential of base terminal with respect to emitter. VCE, potential the collector terminal with respect to emitter. Second subscript represents the common one. So VBE, base with respect to emitter, it is P-type. NPN, so it should be positive. I'm forward bias this. So base VB is positive, and N-type collector is also should have positive one, because collector terminal is always reverse biased. So for NPN, N-type collector should be at higher potential. So our VC is also positive. For common base is common to both input and output, emitter input, collector output. Now for NPN transistor, current flow, emitter current comes out of the emitter terminal, out through the emitter terminal. So IE is negative, IC as discussed earlier, it is positive. Now B is common, so the emitter potential with respect to base should be negative, because to make this base, our purpose is to make our base emitter junction forward biased. So N-type emitter must be at a lower potential with respect to common base. So it is negative. And VCB, again, the collector should be, N-type collector should be at higher potential to reverse bias this junction. So VCB is positive. It is common base terminal. And another one, common collector terminal, collector configuration. Collector is common, base is input, emitter is out. So our IE as usual negative, IB positive, because we are considering NPN transistor, and our VBC and VEC should be negative. It should be at higher potential so that the junction is reverse biased, and base collector, base should be at lower potential than collector. So both are negative. So these are the polarities of different voltage drop appearing across on different terminal and the direction of current. For PNP transistor, obviously all this will be opposite one. Now for working, the emitter junction is forward biased and collector junction is reverse biased. So dynamic resistance at emitter junction is very small because it is forward biased, and collector junction is reverse biased, so dynamic resistance is very high. And we see that our collector current is more or less equal to emitter current. A small IE is basically IC plus IP. So if our emitter current is of the order of milliamp, our collector current will also be nearly the same value. It will be in milliamp, whereas the IB is very small. The IB is of the order of microamp. So we can say more or less that in a transistor, a current is transferred to a low resistance input circuit to a high resistance output circuit with almost unchanged magnitude, because our IC is almost equal to IE, and the input circuit is the dynamic resistance small, and output circuit dynamic resistance is very high. So a same current is transferred to a low resistance region to high resistance region without any change in its magnitude. So the name transistor, transfer of resistor. Now I will come to how the gain of transistor in different mode has different value. So injection efficiency, as already discussed, it gives emitter injection efficiency. So it is defined as IN by total emitter current. So the fraction of total emitter current which is constituted by the desired electron injection. So this IN basically gives IC. So how efficiently the emitter injects carriers, and that will depend on this one. And another term, base transport factor B. B is defined as IC by IN. IC by IN. That means this IN injected from emitter into base suffers a small loss due to recombination and appears in the collector site. So this is our IC. And small part is lost here. So this was IN and this is IC. So IC by IN will give the measure of this one. How much component is lost here? So this is the base transport factor. The IN, the electrons injected from emitter side, will travel through the base and will appear in the collector to form the collector current. So this ratio gives basically base transport factor. That means the fraction of carriers injected from emitter into base survives while traveling through the base. The fraction that survives will constitute IC, collector current. They are not undergoing the recombination. So our base transport factor is almost equal to 1, because the recombination is, we will try to make this recombination loss as small as possible. Only then the injected carriers will be collected from the collector, and that will determine the quality of the transistor. Is it clear? Now we will consider different current gain. In common base mode, emitter is input, collector is output. So the current gain represented by alpha is output current IC by input current IE. Now output current IC is B into IEN. আমরা define করলাম base transport factor. IC is B into IN. The fraction of injected electrons appearing at the output, that is BEIN. And I is IN plus IP. It has two components. So B and IN by IE. This one is gamma. This one is gamma. So the current gain in common base mode is simply product of these two parameters, base transport factor and emitter injection efficiency. So we see that alpha is B gamma. We see that B is less than, but of the order of 1, close to 1, which is B, the fraction of injected carriers that travels through the base and successfully reach the collector site. So it is less than 1, because since that is a physical layer, recombination must be there. We can make it very small, negligible, but still some non-zero recombination will be there, and that will make B always less than 1, but it is more or less of the order of 1. Similarly, for in emitter injection efficiency, because we cannot ignore this term, we can make it very small so that entire emitter current is formed by this one. But since we are applying some forward bias across this junction, it can be made very weak component, but it will always be there. So that also makes gamma always less than 1, but more or less, and is very close to 1. So alpha, being product of these two, will always be less than 1, but very close to 1. B and gamma will be very close to 1, and they will make alpha also very close to 1. That means our IC is roughly equal to IE. If we ignore the loss in the neutral base. Now in common emitter mode, current gain beta will be the output current. Emitter is common. So emitter is common. So base is input and collector is output. So the gain will be output current by input current, IC by IB. And what is IC? IC is BIN in terms of base transport factor. It is BIN. And IB. What is IB? IB, the current, base current, it will have two components. One part that recombines the holes that will resupply the holes lost due to recombination, and the other portion that is injected across the base emitter interface into the emitter. So this is IEP, whole component of emitter current. And what is this? This is BIN, base transport factor into the injected component of electron. That is IC. So 1 minus B into IN will be this one. That is lost, that cannot survive while traveling through the neutral base. So this component is 1 minus B IN. লিখছি না তো, কি clear? Why we take this? IB has two components. One, the component hole injected from base to emitter, and the other is the holes lost by decombination. And all these loss should be compensated by the supply, and that constitute the base current. BIN is the carrier's injected IN that reaches the collector. So 1 minus B will be the injected electrons that are lost while traveling through the neutral base. And they are lost due to recombination with the holes in that neutral base. So these holes and these holes, these two sources of loss should be compensated by the battery. So IB has these two components. Clear? Thus beta is BIN by this one. So IEP plus IN minus BIN. So BIN by this is the total emitter current. So IE minus BIN. Now divide the numerator denominator by IE. So here it is BIN by IE, and here it is 1 minus BIN by IE. So we get B, that is gamma. So B gamma divided by 1 minus again B gamma. So we know that alpha is B gamma. So our beta becomes alpha by 1 minus alpha. So this is the relation between alpha and beta, where alpha is gain in common base configuration and beta is gain in common emitter configuration. So they are related by this one. So you can express beta in terms of alpha like this. Again, for alpha in terms of beta, we write this as 1 minus alpha by alpha is 1 by beta. So add 1 both sides, and we will get alpha is beta by 1 plus beta. So these are the relations. Now alpha can have value 0 to 1 because it is product of these two terms, where each of them is maybe very close to 1 but always less than 1. So if you consider this is 1, then maximum value of alpha can be 1. So alpha can have values between 0 to 1. So we are plotting alpha along x-axis. So for different value of 0 to 1, we can calculate the value of beta from this. And we see that beta can be 0 to infinity. For alpha 1, it is infinity. For alpha 0, it is 0. So alpha, range of alpha is this, 0 to 1, range of beta is 0 to infinity. So a very small change in alpha causes large change in beta. Say our alpha is 0.9. Then beta will be 0.9 by 0.1. So beta will be 9. If alpha becomes 0.99, then beta will be 0.99 by 0.01. So beta will be 99. So from small change in alpha, 0.9 to 0.99, beta changes from 9 to 99. So small change in alpha always gives causes large change in beta. And to make alpha very close to 1, B and gamma must be close to 1. So what will be the criteria so that our alpha will be very close to 1? We'll discuss this thing. Before that, see here. For alpha, beta changes, and for small change in alpha, there is a large change in beta. And that is particularly more important when alpha is very close to 1. Then it increases sharply. If it is 0.999, then it will be 999. So like this, more closer the alpha to 1, beta will be larger. So we should make alpha very close to 1 so that we can get a large value of gain, large beta. Now to make alpha close to 1, B and both base transport factor and emitter injection efficiency must be close to 1. Now to get B close to 1, what should we do? Base with W should be less than LB. I am right. I write this as LB so that it is neither for NPN nor for PNP. This is the diffusion length of minority carriers in the base. Here for NPN transistor, the injected carriers is electron, so it is Ln, diffusion length for electron. So for PNP transistor, it will be LP. So LB is the diffusion length of minority carriers in base region. So to make B close to 1, base width W will be taken as base width is much smaller than the diffusion length of injected minority carriers. That means a very small portion of probability that the injected electrons injected from emitter side will pass through the neutral base with negligible recombination. This is the length that they can travel without recombination. But that is the average one. So there is some probability that these few electrons will recombine with this one. So by keeping the base width very small, we can improve the base transport factor. That means our base layer should be narrow. Again, we will make W very small. Again, we can make LB large. It will further improve B tends to 1. So to make LB large, the base region should be made as pure crystalline as possible. That means there is no possibility of trapping of minority carriers. Base material should be pure crystalline. Otherwise, there will be some defect states and that will trap the injected carriers and they will be lost. And they may help to recombination if they behave as recombination center. So whether it is a trap or recombination center, our base injected electrons will be lost while passing through the neutral base. So we should make base region very thin and base region should be, quality of this crystal should be high, large, and again our alpha recombination time tau depends on 1 by majority carrier concentration. Yes. So reciprocal of majority carrier concentration for that region. So if our doping of this base region becomes very small, then also the recombination probability will be less and injected carriers will pass through the neutral base without significant recombination loss. So base should be thin and base should be lightly doped to make B tends to 1. Again, we will have to also make gamma tends to 1 so that our alpha becomes close to 1 and that will give large beta. So to make gamma emitter injection efficiency as 1, the IEP component, whole component should be very small, should be negligible with respect to IN, electron injection component. This requires again the base region to be lightly doped. So light base doping will also help to increase the probability that a minority carrier survives in crossing the base region. That means base transport factor will also be improved, as I already discussed. So our requirement is base should be narrow, very thin, and it should be lightly doped, as lightly doped as possible, as thin as possible. Accordingly, our alpha will be very close to 1. But these two criteria, some will make the damage of this transistor because narrow base with light doping causes increase in both base resistance and the probability of punch through. We will reverse bias the collector base junction. Now we are making the base very thin and very lightly doped. So the depletion region due to the collector base reverse bias in this junction, the depletion region in the base side will extend faster with reverse bias as it is lightly doped and is thin. So it ultimately, for a certain VC reverse bias, this depletion region for this collector base junction may touch the depletion region of the emitter base junction. And the entire region, there will be only field. They will be swept by this thing. There will absence of neutral base region will make the punch through breakdown or reach through breakdown, and there is no provision of base diffusion, which is the main mechanism of prime mechanism responsible for transistor operation. Injected minority carriers from emitter must diffuse over the neutral base region and then finally they will be collected. So diffusion is the major current flowing mechanism related to a transistor. So if we make it thin and also lightly doped, there is chance that for certain collector base reverse bias, punch through will take place and that will limit the reverse bias that can be applied to the collector of the transistor. That means that will limit the collector bias potential that the transistor can safely handle. এই পর্যন্ত আমি ভেবে দেখো, then I will proceed or I will discuss this portion. তা কিছু বললাম, বুঝলে? ক্লিয়ার হলো? কনফিউজড? না হলে এগোবো না আজকে, অনেকটা একসাথে অনেক কিছু বলা হয়েছে তো।
ম্যাম ন্যারো বেসটা আরেকবার বলে দেবেন।
So we fabricate this 3 layer for transistor. So this is the collector layer, this one. From this to this is the collector layer. Then this is the metallurgical junction. Base collector junction, this is base emitter junction. So this is the neutral base. But as we reverse bias the collector base junction and forward bias the base emitter base junction, we are not considering the thin depletion region appearing across this. So if we ignore that, then this is there lightly doped. So the depletion region will proceed through the within the base. So basically, the neutral width of neutral base region matters for carrier diffusion. Even if this is the original base width, physical thickness of the base layer, but during operation, the neutral base width becomes this one, and it varies with reverse bias in the collector base junction. So as it is reverse bias increases, the depletion region here will extend into the base region. So carrier injection from this side, carrier injection from this N plus heavily doped emitter, the electrons injected into this base. Now this is the neutral region. So here in the edge of depletion region, carrier concentration is 0. So here is a huge large value. So there will be some, the injected carrier profile will be like this, e to the power minus x by ln. So this exponential one. So they will diffuse, will reach here, then the junction field will sweep the electrons and bring them in the collector layer, and due to the external bias, they will be collected. Now, if we see that alpha is big gamma, base transport factor relates the probability that the electrons injected here will pass through this unrecombined, without recombination. They will traverse the base without recombination or nominal recombination. So thinner the base layer, smaller will be the distance they will have to travel. So less will be the probability of recombination. So one thing to improve this, we can make the base region narrow. We fabricate the thin base region, and our doping of the base region is also small. In that case, majority carrier concentration is less, whole concentration is less. So probability of the electrons without recombination passes through this neutral base will also increase. Now we so we write this diffusion profile as e to the power minus x by ln, sorry. I got something problem. এবার বেসটা যদি আমরা থিন করতেই থাকি, আলটিমেটলি কি হবে, সে সাইফার সার্কেল রিভার্স ব্যাক, the depletion region will extend and extend with increase of reverse bias, and for certain value it will cover the entire neutral portion of the base. So here also some depletion region is there. It may be thin as it is forward bias, but it may happen that depletion region extends in this direction and finally is the depletion region on the opposite side. So there will be no neutral base. So the transistor will not operate. The operation of transistor is now also lost, and that value of collector base reverse junction will have that limited value. We'll have the limitation. For collector base junction, if we go on increasing and increasing, ultimately our collector base junction there may be avalanche breakdown, and the transistor of normal operation is not possible. But this breakdown voltage at which avalanche breakdown takes place, the reverse bias of collector base, is the limiting value that the transistor can handle. But if it is made to think that before reaching that breakdown voltage for a smaller reverse bias, this depletion region touches the depletion region of the other side, opposite side. So punch through or reach through breakdown will appear. So if we keep this not so thin, it is quite wider. In that case, that device can handle higher breakdown voltage. Reach through will appear for a higher collector base reverse bias. So, but if we make it wider, then what will happen? Injected electrons will have to cross a wider region. That means their recombination loss will be greater. So our base transport factor will decrease. But one thing here, we are considering this diffusion profile, and we see that problem e to the power, the profile will be, it will decreases exponentially. এটা যদি আমি x direction ধরি, then with distance in the neutral base, the injected excess carrier follow this profile. So it is 1 minus x by ln and higher order terms. We have our this x for this region with this w. So if our w is quite small, much smaller than our w ln, then we can safely ignore the higher order terms, and we can approximate this region, this profile, as this profile is simply as a straight line. It will simply be a straight line. For this, we will join these two regions. Across the neutral base, it will be a straight line. এখানে এটা হওয়া উচিত ছিল শান্তি। So it should be a straight line. Then the concentration gradient will determine the diffusion current, and we make this in minor area profile, we consider it as a straight line because we have purposely made our base with W as much less than ln. Straight line money, I am not considering any loss. The constant slope is maintained. So by taking base width very small compared to its diffusion length, we are basically considering the recombination loss very small. So the minority carrier profile within the base will be approximated by a straight line. So our requirement for large beta is alpha should be close to 1. That means both base transport factor and emitter injection efficiency should be very close to 1. For base transport factor, we make the width of depletion region, base region very small compared to the diffusion length of minority carriers. So the probability that they will not, without recombination, they will survive decreases as this so made smaller. In that case, the probability of recombination will also improve, and that will also improve the emitter injection efficiency. This injection of hole from P base to N plus emitter will also be weaker. for light doping of base. So these two requirements, base should be thin and base should be lightly doped. So if we can make it thinner and thinner and thinner, and doping level is also made smaller, in that case, that probability of reach through or punch through breakdown will appear, and that limits its operation. So transistor as a switch, if the switching voltage, the reverse bias, the reverse voltage should be limited. So that is also the limitation of the device. ক্লিয়ার? কে বলে জিজ্ঞেস করেছিলেন?
Yes, ma'am.
না, আজকে আমি আর নতুন পড়াবো না, এগুলো একটু মাথায় ঢোকা। 47 নাকি পড়িয়ে দেবো স্ট্যাটিস্টিক্সটা? নোটটা দিয়ে দেবো। বলবো আর একটু? 47 এই পর্যন্ত বলেছে, ঠিক আছে, এইটুকু বলে নি। So static characteristics of BJT. There are two types of static characteristics: input static characteristics and output static characteristics. For this one, সোজা সহজ জিনিসগুলো একটু বলি। So assumptions. To explain static characteristics, we will assume this thing, that cross section of BJT, আমি আমার ক্ষেত্রে NPN, should be uniform, because we will calculate the current, so that should be J current density into A. So cross section should be uniform all through the structure. Electrons injected in base diffuse over the base region, and the field across the base is small enough so that there is no drift. What does it say? We have applied forward bias in the base emitter junction, reverse bias in the collector base junction. So we normally assume that the applied voltage, external voltage, appear across the depletion region, because they are the resistive portion of the device. In case of diode, we have assumed that. So net drop across the neutral region is negligible. So that drop appears across the depletion region only. But in our case, we are keeping the base region lightly doped, so it may offer some resistance. So a portion of the applied bias may also drop across the base region. That means that carriers that are injected into the base will also experience that field. So along with the diffusion, the drift of carriers will also be there. But we are assuming that there is the field across the base is small enough so that there is no drift. We will only focus to the diffusion of carriers across the neutral base. Then injected electron density in base is greater than NPU. What is NPU? Electron concentration in P side. That means within base under equilibrium. তার মানে যে minority electron concentration P type base, that should be much smaller than the electron density, injected electron density in base. But the injected electron density in base, that means N, electron in P side. Now we are not considering 0, because now we have applied bias, so it is not equilibrium value. So this NP should be much smaller than PPO, that means majority hole concentration in P-type base. So injected electron density should be greater than the minority carrier concentration in P-type base, but much smaller than the majority carrier concentration. Otherwise, কি হবে? If it becomes comparable to this or greater than this, that means the conductivity type of neutral base is now inverted. It will make the region to behave as n-type. So injection should be controlled to satisfy these two conditions. And collector injection current is negligible. So these are the assumptions. And না থাক, আমার জন্য মনে হচ্ছে বেশি হয়ে যাবে ডোজটা। থাক, আমি আজকে আর পড়াবো না। এই জিনিসটা আমি আজকে আর ঢুকতে চাইছি না। Okay? So I will send the material and go through that so that you can see, check whether there is any confusion. Then in the next class I will discuss it. ঠিক আছে, কারো কিছু জিজ্ঞেস করার না থাকলে ছুটি।
ম্যাম
এখন যদি আরো বলি তাহলে মোবাইল নিয়ে বসে থাকবেন।
ম্যাম
হ্যাঁ বলো।
ম্যাম ওই সিইও ওই কম্পোনেন্টটা যদি একবার রিপিট করে দেন।
কোনটা?
আইসিইও
ও
যেটা
আইসিইও, আচ্ছা আচ্ছা, ওই রিভার্স কম্পোনেন্টটা। ওইটা আমি স্ট্যাটিক ক্যারেক্টারিস্টিক যখন বলবো না তখন ওটা অটোমেটিক্যালি আসবে। আমি প্রেজেন্ট তো করছি নাকি? স্টপ প্রেজেন্টিং তো করিনি, দেখতে পাচ্ছি কি? হ্যাঁ, এইখানে আমার আইসিইওটা আসবে। এইখানে অটোমেটিক্যালি আসবে, তখন আমি এই যে এখানে এটা বললে তখন লজিক্যালি সুবিধা হবে। হ্যাঁ, এইটা হয়ে যাক, নেক্সট দিন এই ক্লাসটা, তারপর যদি কনফিউশন থাকে তখন ডিসকাস করব।
ওকে ম্যাম।
এখানে যখন বলছিলাম তখন বেসিক্যালি আমার বেসটা কিন্তু কমন। কোথায় ছিল আইসিইটা? এটা বলছো না? তার মানে বেসটা যদি কমন থাকে দেন ইট শুড বি কারেন্ট উইথ কমন বেস মোড উইথ এমিটার ওপেন, মানে জিরো input current. That means it should be ICBO. It should be ICBO. ও আচ্ছা আচ্ছা, ঠিক। দেখো, যদি আমি এমিটারটা কমন নিই তখন কি হবে? বেস ইনপুট। হ্যাঁ হ্যাঁ, যখন ধরো এইটা তো আমি বললাম ডিফারেন্ট কনফিগারেশন উই ক্যান ইউজ ইট। নাও উই আর ইন্টারেস্টেড ইন দিস কম্পোনেন্ট, the small current component flowing through this reverse bias collector base junction when there is no injection, when all other components are absent. Only then the small component will come into picture. So for this is this current generates due to thermal energy across this reverse bias collector base junction. So if our emitter is common, then this is input, collector is output, this one. Okay, then your reverse bias across this collector base junction and this thermally generated current will flow through this reverse bias junction. So when input common emitter mode, only for this component. Here এটা কমন বেসেও হতে পারতো বোধহয়, সেটা আমি বুঝতে পারছি না। এইটা ধরো এখানে কমন বেস হলে the reverse bias applied is directly visible. And this junction is reverse biased. With emitter open, we will get the thermally generated component here. That means it should be ICBO with input open. In this case, base is open. So reverse bias is between collector and emitter. within which there are two junctions. So I think it will be more direct. It should be ICBO for বোঝার জন্য at least. Component নেই, absence of this. I think it should be ICBO. দেখে নেব পরের পোর্শনটা। It is the current common base mode, only this junction will appear isolatedly, whereas here you consider this one, but bias is VCE, where a part of it will appear across base emitter and rest across collector base. Whereas in common base configuration, the reverse bias is directly appearing between this common and output terminal. So I think it should be ICBO. ঠিকই পয়েন্ট আউট করেছো, মোস্ট প্রবাবলি আমি ডাইরেক্ট দেখে তবেই কনফার্ম করবো।
ম্যাম
হুম,
ম্যাম তাহলে কি ওটা বেসে থার্মাল এনার্জির জন্য থার্মালি জেনারেট ইলেকট্রন ফ্লো ফ্রম বেস টু
E2
কালেক্টর,
হ্যাঁ,
কারণে
আর ইও ফ্লো করছে, হোলও ফ্লো
আচ্ছা
করছে
তার মানে
from base collector to base, দুটোই তো। Junction
হ্যাঁ,
electron hole pair will be generated, so both electron and hole component will be there, and some will give the current. That will depend on temperature. We always want to have control on the device operation, electrically controlled. সেই জন্য দেখো, আসলে আমি তোমাদের ওই পোর্শনটা ইন্ট্রোডাকশনটা বাদ দিয়েছি। বেসিক্যালি একটা ডায়োড, তার রিভার্স ক্যারেক্টারিস্টিক কি? ইন্ডিপেন্ডেন্ট অফ রিভার্স বায়াস, কনস্ট্যান্ট কারেন্ট। সো ইট ইজ অ্যাজ ইফ আ কনস্ট্যান্ট কারেন্ট সোর্স where the current will flow, whatever be the voltage across it, current will be constant. Think the current reverse characteristics of a diode. Now, this behaves as a constant current source. So, if we want to use this constant current source, basically the magnitude of current is too small due to thermally generated carriers, so of the order of microamp, nanoamp. So it can be used as a constant current source, but its amplitude is too small. So if you want it to use as a constant current source, so that its current is of significant magnitude, and we can exert some control over the current. Then that means first thing, if we increase the temperature, then the reverse current across a reverse bias PN junction, the current will increase. But in that case, our device becomes temperature control. That means for operation of the device, you will have to put the device into an oven. So that is not acceptable. That's the cumbersome. The arrangement will be cumbersome. So always we want our devices to be electrically controlled. Now, if we can electrically control that magnitude of current, which is independent of voltage, then we can make the current magnitude is also quite large, then it will be of use. So we basically were considering this one. It was the thermal generated carrier. So if we can increase, দেখো এই কম্পোনেন্টটা কিসের উপর ডিপেন্ড করছিল? আমি বলেছিলাম যে ওই যে জাংশন ফিল্ড থেকে যে মাইনরিটি ক্যারিয়ার যাচ্ছে, that does not depend on the slope, does not depend on the field. That depends how many minority carriers are being generated near the depletion region. How many carriers are available to fall downhill, potential energy downhill. The magnitude of current depends on how many carriers are available. That means on temperature. Now, if we can introduce carriers on the edge of the depletion region on the other side, then carrier current will also increase, but it is still independent of this because mechanism is same. So we place another N plus slab here so that they will inject the carrier which will appear on the edge of the depletion region. Now they will readily come flow across this depletion region and will make this current larger. So this is the original thermally generated component. But introducing an additional layer to this, we are increasing the reverse bias current for this PN junction, which is independent of applied bias. বুঝতে পারলে না ঠিক না? এখন তো ক্লাস আছে, নেক্সট দিন তাহলে আমি বলে দেবো, আর নাকি এখন একটু ছবি আঁকা যাবে? আচ্ছা আমি নেক্সট দিন ক্লাস, হ্যাঁ সেই নেক্সট দিন একটু মনে করে দিও যে কনস্ট্যান্ট কারেন্ট সোর্স, ইলেকট্রিক্যালি কন্ট্রোল কারেন্ট সোর্স, যদি আমার মনে না থাকে ডিসকাস করে। ওকে, থ্যাংক ইউ।
থ্যাংক ইউ ম্যাম।
Thank you.
Thank you.